Welcome to the class of Magnetostatics. This lecture is for Sem 2. By now we know that the magnetic field can be expressed in terms of the current density vector by the following expression: B of R is equal to mu naught by 4 pi J of R prime d tau prime by R curly R. We know that this, if you have a coordinate system where you can express the source coordinate of any arbitrary substance having a current density vector Jr prime. So if this is R prime vector and you want to find the field at the point P, which is R, and this is curly R. Okay, so curly R is R vector minus R prime vector. This is the expression for the magnetic field in terms of the current density vector. We have further used this particular expression to prove that divergence of B is equal to 0 and curl of B is equal to mu naught times J, because this has a physical meaning of the absence of magnetic monopoles. The divergence-less vector, the magnetic field, is a divergence-less field, and this particular expression is for the Amperes circuital law. This is called the differential form of Amperes circuital law. Which in integral form is known to us from our 12th course, which can be arrived at by using a simple vector calculus. We know that curl of B dot, if you take ds to be the elementary area of any current loop, and you take the surface integral of this curl of B, then that would be equal to mu naught times J dot ds of any arbitrary current loop, any loop having a current I. So this is the area of cross section S, and any small area can be called as ds, and ds has a direction normal to the plane of the loop. So we can always write this to be equal to B dot dl, where dl is the elementary length of that particular loop, and that would be equal to mu naught times the current enclosed. This is what we had learned previously in our 12th course, and this is something new which can be called as the differential form of Amperes circuital law. We would now like to use this particular expression for the Amperes circuital law to find the magnetic field for different cases. Let us first of all use Amperes circuital law to find the magnetic field in the case of a straight wire. Okay, that is an infinite straight wire. Calculation of B using Amperes circuital law. Which actually states, the physical meaning of this particular expression is that the line integral of the magnetic field around a closed loop is basically equal to mu naught times the current enclosed. So let us start with a simple case. The first one is an infinite straight wire, or a wire which is carrying a current I, and we enclose it by an Amperian loop. We call that as an Amperian loop. And if we want to find the current enclosed, then let the radius of this loop be A. Then we can say B dot dl is equal to B into 2 pi A, because the direction of dl, the elementary length dl, and the direction of the magnetic field being the same, we can write it as, and this should be according to Ampere's circuital law, mu naught times I enclosed, which is enclosed by this particular loop. So we can very easily write B to be equal to mu naught I by twice pi A, and if one wants to write the direction, then mu naught I by twice pi A, and if the direction along this is phi cap, okay, then this is given by, this is the expression which we have arrived using Bart-Savart law. We can equivalently use another form to first of all calculate the vector potential, the magnetic vector potential, which is given by B to be equal to curl of A. So one can calculate for the same problem, if one wants to evaluate A, we can calculate A, and it has been shown previously that if B according to Bart-Savart law is given by mu naught by 4 pi J d tau prime by R, where tau prime is the elementary volume, then the corresponding A is given by mu naught by 4 pi J J by J into dl, okay, dl prime, the elementary length, by R. I dl, sorry, this should be I into dl, okay, that is fine. J d tau can be written as I dl prime by R. So if one wants to calculate the value of A for a straight current carrying conductor, let us consider a case of straight current carrying conductor like the previous one which we did just a few moments ago. We have a current carrying conductor which is having and we want to find the magnetic field at a point A, perpendicular distance is A. At this point we want to find the field, and we take this direction as the Z direction, so that at any arbitrary length which was called as dl prime, this can also be called as dz prime, okay. And if one wants to evaluate A, which is equal to mu naught by 4 pi, and I is the current flowing through this, I is the current, and dz prime divided by R is the distance from the source point to the field point, I call this as R, and this R has a magnitude of, if I call this as Z, not Z prime, call it Z, okay, dz. So the distance from this, I call this as the origin, my origin, this is the Z. So R would be equal to root over of Z square plus A square. So this is equal to root over of Z square plus A square. And if I have a finite element which goes from origin to minus of, let's say, L1 to plus of L2, minus of L1 to plus of L2. Then we can integrate it from minus of L1 to plus of L2. The Z variable goes from minus of L1 to plus of L2, my origin being at the point O. Okay. So A at the point R is the point P. The vector potential at the point P can be evaluated like this. So mu naught I by 4 pi, and you can always write this to be an the integral to this. This is a standard integral which can be written as ln of z plus root over of a square plus z square, starting from minus of L1 to plus of L2. Okay. So we can very easily substitute the limit mu naught I by 4 pi and ln of L2 plus root over of a square plus L2 square minus, so this would be divided by minus of L1 plus root over of a square L1 square. And the direction would be along the direction of the current, so the direction would be along z cap, because this is a vector quantity. Okay, so we can just now for cases where we have for the wire for a wire of length twice L running from twice L, so from minus L to plus L, if we have an equidistant lower part and upper part such that the expression becomes much simpler, where L1 is plus L and L1 is minus L and L2 is plus L, then the expression for the vector potential goes like mu naught I by 4 pi z cap ln of L plus root over of a square plus L square divided by minus L plus root over of a square plus L square, which can be simplified to be mu naught I by 4 pi z cap and ln of 1 plus a square by L square whole to the power half, and minus 1 plus a square by L square whole to the power half. And in the limiting case of where A is much less than L, for the limiting case of A much less than L, we can say A square by L square is much less than 1, and we can apply binomial expansion such that AR becomes mu naught I by 4 pi z cap and ln of 1 plus 1 plus a square by twice L square, okay, divided by minus of 1 plus a square by twice L square, okay. So this cancels out and you are left with something like mu naught I by 4 pi z cap ln of 2 plus a square by 2l square divided by a square by 2l square, which can again be simplified as ln of 4l square by a square plus 1. And since a square by l square is much less than 1, so l square by a square would be much greater than 1. So one can write log of 1 plus a very large quantity to be approximately equal to mu naught I by 4 pi z cap ln of 4 l square or 2l by a whole square. Okay, so that makes it mu naught I by twice pi ln of twice l by a, okay, and z cap. This is the expression for the vector potential, and we can arrive at the expression for the magnetic field by simply taking the curl of this. So if I say we want to take the curl, then this is r cap, theta cap and phi cap, the three r cap, r theta cap, and this should be in cylindrical coordinate because this is going to give us okay, and there is something we must replace also over here. This is a z cap, so this would be del del r, del del theta and del del z, okay, and this would be 0, 0 and az. Okay, so az is something which must be written in terms of r because the expression is given by z cap would be 0, and here this is not a function of theta cap, there is no theta, so what is left is basically something like r cap into no, r cap is not r cap del del theta of az and theta cap, okay, r theta cap, okay, and del del r of az. This should be the case because the vector potential is only a function of the distance, and if we want to write az in terms of r, then this should be written as mu naught I by twice pi ln of twice l by r. Okay, we can make this distance as a r distance because for this should be r. Okay, make it r, that would be fine. Make it r, then it would be all r's. R. So all this can be replaced by r, where r is the variable distance. Okay, now it's fine. So I hope that won't confuse you, since I have replaced all the a's by r. R is a variable distance, so that we can take a differentiation, and now we can very easily write minus of r theta cap, where theta is the angle for this, which again can be written as phi cap. That would tally with our previous analysis, phi cap. Okay, make it phi cap, del del phi, r phi z, those are the cylindrical coordinates. So r phi cap and del del r of this quantity, which is mu naught I by twice pi ln of twice L by R, and that gives us minus of R phi cap, and mu naught I by twice pi del L R of this is going to give us 1 by twice L by R into minus of twice L by R square. So that gives us this to be minus minus cancels out, and there is 1 twice L by R cancels out, and what we are left with is twice L by R, and this is minus of twice L by R square. So this is going to give us mu naught, this should be phi cap, right? This shouldn't be, otherwise it's not going to tally. So mu naught I by twice pi R phi cap. Okay, so this is the expression for the magnetic field, which can again be arrived at by using the vector potential concept, calculation of the vector potential, and then from there you can take a differential to calculate the magnetic field. Although the mathematical analysis seems quite tedious to calculate this, it's rather easy to go away with Ampere's circuit law in integral form, and it's a bit difficult first of all to calculate the vector potential and from there to calculate the corresponding magnetic field by taking the curl of the vector potential. Let us jump on to the other cases where we can again use the Ampere's circuit law to evaluate the magnetic field. Let us try to find the magnetic field using Ampere's circuit law for an infinite solenoid. So the case 2, which are actually referred in your new CBCS course. The first one was an infinite straight wire, the second one is an infinite solenoid, and infinite solenoid where you need to use this Ampere's circuit law to calculate the magnetic field. Let's say this is our solenoid, okay, and the current is flowing like this. We have this solenoid and we want to calculate the magnetic field. We have let's say, first of all, consider an Amperian loop. Again, we are considering an Amperian loop 1. Call that as Amperian loop 1. And if this is labeled as PQRS and we want to calculate the line integral of B dot dl to be equal to mu naught times I enclosed, you can see that this loop doesn't enclose any of the current because the currents are flowing through this in the case of the solenoid. So we can take this to be 0. Okay. And if I say that this is at a distance r1 and this is at a distance r2 from the center of the loop, then we can write the left hand side to be equal to B dot, if I say this to be B into, this can be written as PQ, okay, dot dl plus B dot dl into QR plus B dot dl. The left hand side can be evaluated like this: B dot dl into RS and B dot dl into SP, and this should be equal to 0 because no current is being enclosed by this Amperian loop. So what is the value of, if I say that this particular length is L, this is also L, and these two are sufficiently small, although they are not going to contribute, because the direction of the magnetic field and the corresponding direction of the elementary length are perpendicular for QR and SP, okay, because the magnetic field for such a solenoid would be parallel to the axis in this particular case. So here we can write for PQ it would be equal to B of R1 into L, okay, plus this should be 0, again this should be B of R2 into minus of L, because this is in the opposite direction, plus 0, so that gives us B of R2 to be equal to B of R1. So we have a uniform magnetic field in the region which is very close to the solenoid, but that is the Amperian loop is outside the solenoid. That much can be concluded. Let us again consider another loop which is partially within this particular solenoid. So we can write this to be equal to again P, Q, R, S, okay. And again we can evaluate or use the Amperes circuital law to calculate the magnetic field. So in this particular case, if again L be the length of the loop and the width of the loop is not so much required, because for those cases the magnetic field would be perpendicular to the elementary length, the direction of the elementary length. So in that case we can say B dot dl for the Amperian loop 2, okay, Amperian loop 2, this is for loop 2, okay, and this was for loop 1. For loop 1 it was outside, so it was equal to 0, but for loop 2 it would be equal to, if n be the number of turns per unit length, into L into I. If I be the current flowing, then the this is the number of turns per unit length. So how many turns of current are there multiplied by the length. So the left hand side can be again written as B dot dl PQ QR RS and SP, okay, and that is equal to NL into I. So there should be a mu naught also, mu naught NLI, okay, because the original law says that B dot dl is equal to mu naught times the I enclosed. Okay. So in this particular case we can say for PQ it would be equal to B into L, okay. For the second case it would be QR would be equal to 0. For RS it is again something which can be called as 0, 0, and that is equal to NLI mu naught, okay. So from here one can write B is equal to mu naught in I, and if one wants to have a direction B, then it would be equal to mu naught in I times, if I say that the current is flowing along my right hand curling of the fingers, then the corresponding magnetic field would be along the axis. If it is along this, then the thumb would point the direction of the magnetic field. So this is one of the case where we have used the Amperes circuital law to find the magnetic field due to an infinite solenoid.